Okay, so let me at the outset start by thanking Adib, who was very kind enough to switch his talk with mine, primarily because my talk is more interesting. No, because I had a family emergency and I have to leave tomorrow, so he was very kind enough to switch my slot with his. And also, let me thank Subhro and Sergej for putting together this beautiful conference and school. Okay, so I'm going to talk a little bit about some experiments we have been doing at Bangalore. So this is going to be a topic called as arboreal quantum phases. So the co-conspirators are Nandagopal Manoj, who is now a student at Caltech, and Gurkirat Singh, who was a student at IIC and who has just started his graduate study at MIT. And Surajit Bera was also a student at IIC. He's now a postdoc at one of the CNRS labs. And I've been generously funded by SCRB, and now it has become ANRF. This is our National Science Foundation equivalent. Right. Okay, so what am I going to do in the next 40 minutes or so? Very quick, big picture. Actually, you don't need this for this meeting at this stage because a lot of this has already been seen. So what I'm going to talk about is, so this meeting is about generalized symmetries and anomalies and all that stuff. So I'm going to introduce a small addition to this, generalized arenas. So what I want to talk about are quantum phases on systems that don't tessellate a manifold. So that's going to be the story, okay? So our main motivation is to explore phases whose infrared description, at least to my knowledge, does not have a quantum field theory underlying. So that's what we're going to try and do, okay? So I'll talk two examples. One is free fermion phases, and the other is these topological and fracton ordered phases. Okay, this slide I don't think is needed, but let me just go through it. As you have seen many times in this meeting, one of the goals of current research is to understand how to classify phases, and entanglement has become a very important concept in this. And we have short-range entangled phases and long-range entangled phases. And examples of short-range entangled phases are topological insulators, and long-range entangled phases are these things like toric code, a fractional Hall effect, and so on. Okay, so I'm going to tell you what these arboreal arenas are. So if you know the word arboreal meaning tree dwelling, right? Arbor means wood, and arboreal means tree dwelling. So you might wonder, why do you want to go back to the trees? We came back down from the trees a few million years back, right? Why are you climbing trees back again, right? Okay, so you see, I just mentioned that a lot has been understood about lattice models for free fermions and topological phases and fracton phases, etc. And if you look at those models, you will see that those models are all constructed on lattices that effectively tessellate a manifold. They dice up the manifold, and then you can work with that. So if you take, for example, your famous toric code, you can, if you look at its long wavelength field theory, you can write some kind of Chern-Simons theory for it with some matrix K. And you can describe its, at least physics in one side of the, say, Z2 gates theory using that. And we have seen a lot about modular tensor categories and classifications, etc. And I also discussed in my own school level lectures that, fracton phases can also be described by field theories using tensor gauge fields, etc. So this manifold arena has advantages. For example, we can study them using quantum field theory. And it has issues. So for example, if you take the toric code, you know that these monopoles create havoc at finite temperature. So that's so you can have proliferation of defects, etc. So our motivation was to first address some of these issues. And the question is, can we see some new physics if you go beyond manifolds? So now, if you want to straight away jump from manifolds to non-manifold systems, and you want to work with some discrete solvable models, then the first thing you'll think of is trying to put theories on graphs. Now, if you ask, what can you do with general graphs, then that becomes very unwieldy because there are all kinds of graphs, right? So what we decided to do was, we decided to start looking at graphs which are tree-like, which means that we had two desiderata. The first is, whatever model we construct, there must be a manifold limit to that model. So if I put a parameter in the model to be something, then I should get a manifold back. If I change that parameter, then I should be non-manifold. So this is the idea. So trees are a very good example of that. And so we started working with these tree graphs. And the reason for doing this kind of stuff is, there's a lot of work that is going on in these synthetic quantum systems where you can construct all kinds of exotic connectivities of qubits and atoms and whatnot. So this is one of the things that particularly inspired me. So this is hyperbolic space that is, some hyperbolic manifold. This is a manifold system that was realized in this group. And so these are possible. Okay. So what are these arboreal arenas I'm going to talk about? So I'll come back to these things later. For now, the simplest arboreal arena that we can think of is simply the Bethe lattice that we have seen many, in the early condensed matter courses, right? People show these things, right? So what do we have here? You have a site which is coordinated by 3 other sites and so on. And the way we construct these systems, at least in our work, is we try to have some notion of translational symmetry. What do we mean by that? So if you look at this site, it has the same kind of neighborhood as this site. So this will keep the graph nice and simple in the sense that there is some notion of translational symmetry. I will come back to this point later. Okay. So the first kind of graph that I'll be talking about is this k-coordinated Bethe lattice. And then I'll talk about these things which may not be familiar to many people. So these are called hypergraphs. And you see, again, I would like to quote the thing that I said about Gates theories. So we didn't go looking for hypergraphs, the hypergraphs came looking for us. So they will turn out to be absolutely necessary for us to construct the theories that we want. Okay. So these are called hypergraphs. I'll come back to them later. Okay. And in all of this system, I'm writing this is a crude statement. Every site is identical in the sense that the environment of every site, at least visually, is the same. Right? So that's the idea. Okay, good. So first thing I'm going to do is I'm going to warm up with some simple things like free fermion models on these systems. So what is the simplest free fermion model one can construct? Okay, so you see, I have a 3-coordinated Bethe lattice here. And what I'm going to do is I'm going to think of a generalization of the SSH model, right? So what do I have? I have three links. And on each of these 3 links, I'm going to give a different hopping T1, T2, and T3. Okay, and this just translates out, right? So you see that every site will have 3 different links with 3 different hoppings. Okay, all right. So that's the system, and I want to understand what is the phase diagram as a function of this T1, T2, T3. I can discuss results for any value of P. And if I stick P equal to 2 in this, that will produce for me the SSH chain. So I recover the manifold I want by putting P equal to 2. Okay. So this is well known. It's actually undergraduate physics now. But I have to revise a few things because these things will become important for me. So you see there's a hopping strength T1 here and T2 and so on. So if T1 is stronger than T2 the way I've constructed, this will be a trivial phase. And if T1 is less than T2 in magnitude, then I'll go to the topological phase and it has these edge excitations. And you have these protected zero energy modes. Well known. Okay, what is interesting to note is that I can also look at this phase transition from the entanglement perspective. So in some way of computing entanglement for this, which is, looking at these 2-point correlations, you can actually characterize entanglement spectrum by a number between 0 and 1. And if you look at this trivial phase, you will see that the entanglement spectrum has some gap, right? So that's the gap I'm showing here. And this is the phase transition, and then you see that the entanglement spectrum is gapless. And if you go to the topological phase, you see that the entanglement spectrum has, okay, the way we have plotted this, it's at there are 2 eigenvalues near 0.5, right? So if you can shift it and make it 0 if you wish. Okay, so you get these 2, so this is a signature of the fact that you are in some topological phase. Okay, and this cut is made in a suitable place so that you are in the correct unit cell, etc. So if you think of this as the unit cell, you have to make the cut here, right? So that's how this cut is made. So the entanglement carries the signature. Now, what is the main thing that I want to convey? The main thing that I want to convey is that if you think of this as a phase transition in entanglement, this phase transition of the entanglement takes place at exactly the same parameter point in the coupling space where the gap closes and there is the thermodynamic phase transition. So the entanglement transition coincides with the thermodynamic phase transition. Right? So this is the point, this is why I wanted to revise this point. And of course, if you want to study this in the long wavelength, you just write down a Dirac theory, and that's also valid. Okay, what happens? Yes. Yes, yes, absolutely. There are two of them. They will correspond to these two edge states that you have. These things, but they're gapped. They're not at zero energy. So in this language of writing entanglement, the zero energy will be at half. There will be zero energy modes, and this is the gapless, there is like a gapless spectrum at the transition point. Okay? All right. Okay, so this is the phase diagram for P equal to 3. Okay? And you see that there are three distinct phases, I1, I2, and I3. They're all gapped phases, and what is being plotted here are the density of states. Okay? And what you can do is, the way this is plotted is pretty much like what is done for the Kitaev honeycomb model, right? This is for 3 parameters. So you can go to this, this material science kind of way of writing concentrations, etc. I forgot what it's called. So for example, if I'm at A1, that is T1 equal to 1 and T2 and T3 are 0 and so on. So if you put a point here and draw, find the areas that are matching the ends, you can find the values of T1, T2 and T3. So in this way of doing this, you will find that the phase boundaries are these. This is the phase boundary. And you see, if I'm along this line, what I have is, I have a set of disconnected chains. So this phase transition point here that's occurring, that's the same phase transition point as you get in the SSH model. The C13, C23, and C12. So these lines are special. They're a set of disconnected manifold-like systems. But anytime you are in the interior of this triangle, you are in a manifestly non-manifold system because you are on this tree. Okay? And now you see, if I'm in this I1 phase, which I'll call as one of the obstructed atomic insulators, I cannot go to I3 through a point phase transition. That means there's no critical point. There is a regime, there's a gapless regime. Right? So this is M is a metallic regime, and that's gapless. Okay? And there is never a direct phase transition from I alpha to I beta, where alpha is any one of these. And this is true for any P greater than or equal to 3. Okay. So that's the first result. Now, if you look at this region, which is the metallic region, I'm going to claim that metallic region itself is 4 distinct metallic phases. Right? So there's an M1 phase, M2 phase, an M3 phase, and an M0 phase. Now, how do I distinguish these things? So you will see that is by using correlation functions. So you could, for example, write down some C dagger C kind of 2-point correlation functions, and you will see that they will have very different characters in these regions. P is the coordination. Right? So for example, this is P equal to 3. Okay, so you get this, and we can actually obtain the equations of these boundaries, etc. That's given here. Okay, all right. So the most interesting thing that happens here, which is what is highlighted here, I'll show it in the next slide. In these regimes, the metal has 0 energy protected edge modes. The metal has 0 energy protected edge modes. Bulk is gapless, but you can get 0 energy modes localized, which will be stable if you just change the hoppings a little bit. Right? Okay, so what is this? So this is a protected 0 energy edge mode. So you see that it will pick a particular one of them depending on which is the strongest and weakest bond. So all these 3 bonds are different, so it will pick a certain way to form the edge. Right? This is in the metal. Okay? Now, how do we characterize this? So we thought a lot about these things. We couldn't come up with some parameter for characterizing these phases until Gurukirath showed up on the scene. And he came up with this thing called as the winding characteristic. So what he pointed out was that you can actually characterize these phases by using a following ratio. So this GZ is the on-site Green's function. So it's the amplitude that if you put a particle at a site, it will come back to the same site. So that's this G of Z. G alpha Z is the same thing, except that you will not be allowed to hop along the alpha link. So you cut that link and find the on-site Green's function again. No. Only on that site. Only here. Right? So yeah, so it can go around, it can go into this side and come back. Right? So this quantity, it does different things in different phases. So for example, you can show that this W alpha will wind the point half when you are in the topological phase associated with that, and will not wind the point half when you are in the trivial phase. Okay? Now here's the most interesting point. If you cross this boundary, the winding characteristic does not vanish. So what am I telling you? I'm telling you that the thermodynamic phase transition where the gap closes does not coincide with this winding number change. Okay? So what's going on here? So I'm claiming that the entanglement transition does not coincide with the gap closing. So what I'm going to argue is that this M1 phase here is actually a phase where, as I'm moving in the M1 phase, there are lots of phase transitions taking place. What are these phase transitions? So, yeah. It'll die, it'll die in a certain way through the system. It will not die with it won't die over some finite length scale because there's no gap. It will go on. Okay, so what I'm showing you here is I'm starting from this B point, which is the phase boundary in the thermodynamic sense. So this side is gapped and that side is gapless. And if you look at the C, you see that if I take this manifold now, there are different types of chains. There is the 1, 3, 1, 3, 1, 3, 1, 3 chain. There is the 2, 3, 2, 3, 2, 3, 2, 3 chain. There are like 1, 2, 3, 1, 2, 3 chain. There are all kinds of different types of chains. So as you're going around in this parameter space, each of these chains differently are undergoing entanglement transitions. So if you look at the entanglement spectrum on one of these chains, it will close the gap at C for one. That is this jump here. Okay, never mind what this is. This sharp point is where the C changes. This D, which is the other one, that will change for another chain. So what we're claiming is, in this regime, you give me any parameter point, I will find you a chain, which is like 1, 2, 3, 1, 2, 3, some kind of, which is closing gap, entanglement gap there. So what you are having is a cascade of entanglement transitions in this regime. Right? And when you reach here, all the entanglement and all the chains is gone, everything has become like trivial, right? And the claim is that there won't be any chain with this, which has any winding transition. So all windings have also vanished when you reach. Okay? So yeah.
Is there a way to characterize the measure of such critical change?
Measure mean you're asking? Okay, you're asking. I understand. So, for example, what is if I could say there are n chains? What is the ratio? Okay, I don't know the answer. Right. So there are, you don't have to cut chains. Also, there can be like random things and all. Right. So I don't. Yeah. Okay. So this is the story. So you can already see that this is very different from what happens in a manifold. Right. So in a non-manifold system, you can have different topological phases, etc. But you cannot step from one topological phase to the other by a simple phase transition, because you have to do the entanglement pattern in different subsystems at different values of the energetic parameter. Okay, so this is something different from what we see in manifolds. Yes? You're asking why this boundary is there? That's not a sharp, I mean, that's, so you see, okay. So what happens is, I'll explain it to you in a different way. So in this, because the free fermion system, the entanglement is completely determined by 2-point correlations. So what you will find is, in this regime, different chains have different length scale of 2-point correlations. When you reach this boundary, all length scale becomes same, and that length scale is going to be determined by the density of states. It's like Kf of our of the free Fermi gas kind of thing. So why that's happening, I don't have a good answer, but that is what is happening. What do you mean by orientation? There is absolutely a consistent way, right? Because you see, I make sure that every site has one T1, one T2, and one T3. But that's some diffeomorphism, right? That's some orientation change, right? But it won't change the topology. That's like how you label the sites, if you wish. Right? Yeah.
So, all these curves, at least one color.
Then become manifold like.
All of them?
All of them will become, if you say make T1 equal to 0, then you will get set of T2, T3, T2, T3 chains. All kinds of coloring. Right? Now this choice of which one you put in, see, that simply saying that, I'm going to go there and I'm going to just turn that thing, right? That's diffeomorphism. Right? Okay. Okay. So that's the story. And okay, so we can, we meaning Gurkirat, always remember. So this problem can be solved for any P. And here is something absolutely that really surprised me. So remember that there were two types of critical points in this phase diagram. There is this manifold critical point, which is the one-dimensional critical point of SSH. And then there is this critical point where the gap closes. So you see at the gap closing point, see that's a semi-metal, right? So there's some power law density of states there. So here's the result. If you look at the low energy density of states along this boundary, so this is now drawn for P equal to 4, right? So it's now some 4 simplex, 3 simplex. So you can do this for any P with whatever simplex you want. So you'll see that the density of states goes as omega to the 1/3. And this is not for P equal to 3, it's for P equal to 4. It is also omega equal to 1/3 for P equal to 3. It's in fact omega equal to 1/3 for any P greater than or equal to 3. So we call this the arboreal universality. So it doesn't matter which tree you are taking, how many branches it has, it's the same thing. And all other parameters, they have the same values. So for example, you can some dynamical exponent that turns out to be 3/2. If you look at the density of states, that will go like this. And all of this stuff, we can look at the singular part of this parameter, you can look at the singular part of the entanglement gap. All of them will scale with the same exponent, 5/2 in this case, irrespective of what P is. P equal to 2 is manifold. Yeah. Yes, I'm aware, yes. 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 You see, so this is a 3 simplex, right? So you see, there is like a wedge inside. There is like a tetrahedron inside. So the 2D version of that will be this line. So along that face, it is that. And if you touch one of the bases, so for example, if you look at this line, that is like a chain and our P equal to 3, but that will have a mixed density of states if you wish. And one of them will be gapped still because the other chain will be gapped. So you will end up getting the same omega equal to 1. I hope that answers your question. Okay, so this is what we have found, and okay, so we are trying to explore this further. So what is the main message here is that if you go non-manifold, then entanglement and energetic seems to go away from each other. So you can have more richer entanglement structure, and energetics will take like become like a sideshow. So that's basically what we are pointing out here. Okay. So we are trying to understand this arboreal universality from some. So if you think about what are the translation groups of these, they turn out to be some free groups, etc. There is some connection to hyperbolic spaces, because if you run P equal to infinity and Q is certain thing, then you can actually recover hyperbolic spaces out of this. And so, or you start with hyperbolic spaces, you can recover trees from here, and so on. So, of course, it will be fantastic if we can classify all the gapped phases here. Okay, all right. So, I hope that there are some experimentalists who have managed to survive fusion categories. So, if they are there, please try some of these experiments. We are trying to talk to as many people as possible to get these experiments going. All right. Now, let me, yes. Sorry, I should.
Electric circuit?
Which one?
The last one.
Electric circuits. No, but you could instead, yeah, that's a very nice question. So we may not be able to produce the entanglement spectrum, but you could try to get that edge mode that I showed, right? So you could, if you create something with some circuit, some capacitors and some LC circuit or something, then you could try to localize like a mode, right? Like it has been done in all the other electric circuits experiments. No, it's a proof for any P. We can expand the equations around. No, that is just the statement. That's a very, okay, maybe I was too poetic about that. So I'm saying that this is where the gap closes and this full region is gapless. But the entanglement transition, there are different entanglement transitions taking place in different subsystems. Are separated, right? So usually in the SSH model, for example, where the gap closes is also where the entanglement will be rewired. So here gap closing doesn't guarantee that every subsystem is become trivially entangled. That's what I mean, at least. Okay. Yes, correct. Yeah, it will be 2-point correlation functions, but they'll change character. Yeah. Okay. So now let me move on to these topological fractal ordered phases. Okay. I have only 11 minutes, so. Everybody, I have shown this slide before, so there'll be a quiz on this afterwards. Okay, all right. There are people whose work I'm quoting here. You can actually show that by unitary depth, finite depth unitary circuits that you can connect some different phases associated with, say, the square lattice toric code and some amorphous lattice toric code. And so in this sense, these two phases are equivalent. Of course, we discussed this. I've discussed this XQ model in fair detail in my own school lectures. So just very quickly, for those who are not here, you write down a model in a cubic lattice, and you write this 12-spin interaction. It's called the cube term, and you can write a certain kind of operators, like what we call A operators, which leave this invariant and so on. And the important thing is that this system will have a large degeneracy, sub-extensive degeneracy, which you can trace to the existence of these Wilson lines. And if you want to think in terms of classification of phases, etc., so usually we'll say that if I have sub-extensive degeneracy, how do I compare two different systems of different sizes? So the idea is that if I can take something that is topologically ordered, like a sheet of topologically ordered stuff here, and I just throw it onto the system with a certain system size, you can do a finite depth unitary on this, and then you can paste it onto this and go to the next system size. Okay. So if this is possible, then you say that these two systems belong to the same fracton order. So this can be done. Okay, and the reason for fractons also was shown. Okay, important thing I would like to revisit, which I had actually rushed through in my own talk. So if you take the Z2 gauge theory on the square lattice, you can see that its dual model is the quantumizing model. And if you take the X cube gauge theory on the in the cubic lattice, you can show that its dual is the phase-izing model. Okay, so this is a very general feature as is shown in this paper. Okay, so now let me go to arboreal arenas. And now I have to discuss these other pictures. Okay, so as we started working on this, we realized that you cannot discuss these class of problems with just simple Bethe lattices. You have to go and read the graph theory math books, and they introduce this notion called as hypergraphs. So what is a regular usual graph? A regular graph is a set of points or vertices and a set of edges that connect them. So here what happens in hypergraphs, the edge can have more than two sides that connect to it. So this whole dash thing is called an edge. It's called a hyper edge, right? So this is 2, 3. That means every side touches two edges, and every edge picks up 3 sides that touch it, right? So this is a 3, 3 hyper Bethe lattice. So this is a hypergraph, okay? So you will see that they will just naturally show up in our discussion, as you will see. And again, like this is the same transparency. So every site is identical in the sense of like some crude idea of neighborhood. Okay. Now, if you wish, the hypergraphs that I introduced in the previous slide, if you think of them as one-dimensional things, I don't mean in manifold dimension, some one dimension like thing, you can construct higher dimensional things if you read those math books, right? So they have a notion of what is called as graph Cartesian product. And they have a nice formal definition of which I'm illustrating by a very simple picture here, right? So take this graph, right? It is a tree, as you can see. There are no loops in it, right? And this is the box product, and this is our little piece of manifold that we have. So when I box this, I'll end up getting this. So what I do is I take this thing and I extrude it along this manifold, and so I'll end up getting this. So what do you see here? You see something very beautiful, which is that all the motifs that you have in regular cubic lattices and all that stuff, all of them will be reproduced here. So for example, I have a notion of a plaquette. So what is it that I'm trying to convince you? You give me any kind of what is called as local Hamiltonians, defined on plaquettes or any sort of reasonable things, I can put them on these arboreal manifolds, arboreal arenas. Okay, so let's start discussing one-dimensional systems. So if you take a qubit model and defined on this integer to the D lattice, you can put it on the arena. So for example, let's start the one-dimensional model. You have this generalized quantumizing models on the hyper Bethe lattice. So what is the idea here? Any link is the product of the number of sites, the Z operators on the number of sites. So if I have hyperlink with n sites, then I will have n body interaction. So here this is 3, so this is 3 body interaction, right? And the transverse field just acts on the site, so it just comes for the right. So if you now write this Hamiltonian on the 3-3 lattice, you see something very interesting. This Hamiltonian has subsystemizing symmetry. So what is the subsystemizing symmetry? You take the subset of red sites here and flip the spins on that. So you will see that will leave the Hamiltonian in there. Right? So you will see that you can construct systems like that, so it has subsystem symmetry. Now, if I take a two-dimensional arboreal arena, for example, I can take the Brock's product of one Bethe tree in one direction, and in the perpendicular direction, whatever that means, I take another Bethe tree. So that is K1 and K2, right? And I can write down the Z2 gauge theory on this, right? Using the box product, because I'll get plaquettes and I can write down the Z2 gauge theory. and I can write X cube gauge theory on the three-dimensional array. So what does this buy you? Okay, here's the simplest Z2 gauge theory on the Arboreal arena is fractonic. Okay, so this is a major punchline. So you can see, so suppose I create a placket excitation on this. Okay, you will see that I will never be able to move this in the tree direction. Remember, this is B3 box B2. So one direction here is manifold-like. If I try to draw B3 box B3, at least certainly I cannot do it, right? Because it becomes some highly non-oriented thing and so on. So you can't draw a picture for that. But you see, if you try to move this placket by flipping this pin, for example, you will create two placket excitations and so on. So this is stuck. It cannot move. Okay. Second thing is, you will be able to see that there is a large ground state degeneracy. So if you in fact truncate this to some generation of the tree, then you will see that there will be some power of generation degeneracy. Where does this come from? It comes from the fact that there are many, many different Wilson lines, right? So for example, this line is a Wilson line. So imagine a tree. So I just maybe, so you see, I can have a Wilson line like that. I can have another Wilson line. There are lots and lots of Wilson lines. So that's why you're getting these large ground state degeneracies also, because there are all these independent Wilson lines that the Hamiltonian has to commute with. I'm sorry?
Wilson line, one color.
Color, you mean?
Yeah.
No, I have picked one Wilson line and drawn it with one color. You can, just to illustrate a Wilson line, but I can have it, so the value of the Wilson line can be plus or minus 1. This does not have subsystem symmetry. This is gauge symmetry. This is this transverse field model on this has subsystem symmetry. This is a full-blown Z2 gauge theory. So what I can do is I can show up here. I can show up here at this site and flip all the spins. That's the A operator. It has the full Z2 gauge symmetry. Right? Yeah, and so I'm just illustrating a Wilson line by drawing this color here. Okay, and now you can write some variational wave functions quite similar to that, and you can show that this thing has confined and deconfined phases, etc. Okay, and many times there are first order transitions. And if you go to X cube model on these three-dimensional arboreal arenas, all magnetic excitations are fully fractonic. There are no, remember in X cube that I discussed, dipoles were planons. There are no mobile magnetic excitations. Everything is completely stuck, right? So you'll see that it's, and it again has a huge degeneracy coming from these Wilson lines and so on. It has also confined and deconfined phases. Okay, now the question is, how do you understand this? How do you understand the fact that the simplest Z2 gauge theory is fractonic? So I'm going to show you that you can understand this by dualities, right? So remember, I showed you that if you take the regular X cube model defined on the cubic lattice, then the dual model will be something with subsystem symmetry. It will be the phase Ising model with subsystem symmetry. Okay, so let's start with looking at some simple dualities. So if you take the generalized quantum Ising model on the Kn Bethe lattice, you can show that its dual is HB on Nk. Right, so you see, the proof is drawn by this picture. So what you do is you make this into some Z operator and the product of Z operator, so that will become this triangle. And whichever are these intermediate sites, you make them sites and put this Z operator as X operator there, and you'll see that the algebra is a different representation of the algebra equation. So you will see that you can map from here to here, right? So this is an example of BK2 is HB23, right? So that's the duality, okay? And this is the very well-known Kramers-Bonnier duality. And I'll just show you quickly that the Z2 gauge theory defined on BK1 box BK2 is dual to the generalized quantum Ising model on 2K1 and 2K2. But remember, the generalized quantum Ising model has subsystem symmetry. So I'm showing you that the Z2 gauge theory, the dual has subsystem symmetry, which is exactly the recipe you need to get fractons in the gauge theory. Right? So you see that this is completely consistent. Okay, so we have worked out a whole class of dualities here. To the best of my knowledge, all known dualities of Ising-like systems is contained in this, because if I put this as the manifold versions here, they will turn out to be the corresponding known results. Okay, and you see there are some S, R and all that stuff. So what is this? There was a question during my talk also, during my school lecture. So if you cut this and make it finite boundaries, then you can truncate the boundary in different ways. There can be smooth, rough boundaries, etc. So you will see that the smooth dual will be rough and so on. There are some very, very nice connections on about this, and so all that's worked out here. So yeah. Okay, now comes the very interesting question. So I have the toric code order which is defined on the manifold. Now imagine that I were to put this, I were to have some kind of toric code on some non-manifold system. So this is BK box B2. Right? Now the question is, are these two the same topological order or are they different topological orders? Okay? So what we did was we used the entanglement renormalization idea, and what we are able to show is the following. If you take B2 box B2, that's just the toric code. So that is in a class by itself. Then there is a second class of topological order, which is one direction is non-manifold-like. So one direction is tree-like, so that is why k greater than 2, and the other direction is manifold-like. And so what you can show is that for any k greater than 2, you can do entanglement renormalization and bring it to k equal to 3. So there is, for whatever k, there's only one topological order as long as k is greater than or equal to 3. It is the topological order for k equal to 3. And now if you do k1 and k2, when both k1 and k2 are greater than 2, so non-manifold in both directions if you like, then it's the topological order of B3 box B3. Okay? The same thing goes for X cube model. So you can do this for X cube model and you can do this. Okay? So this is all done using the entanglement normalization trick. Okay, so we have in a sense classified at least the Z2 topological order in these kind of arenas. And that is one of the things that comes out of it. I've run out of time. So this is the summary of everything that I've said in these topological fraction ordered phases. And just a quick reminder of what I told about the non-interacting fermions. And that is the summary of my talk. So thank you very much.
So the last part when you talk about the analyze the topological phase using the entanglement spectrum, you mean numeric or analytical calculation?
The entanglement renormalization.
Okay.
No, which one are you talking about? The fermion one or the qubit one?
The toric code, but
no, the toric code is done analytically using Julian's paper. Okay. So we use the C0 gates and we just construct a finite depth unitary circuit.
Okay.
And we apply it. So it's very hard to draw these things. We just write down these equations, right? It's extremely hard to draw this. So we apply this kind of, at least it's very hard for me. So you see, so I'm just illustrating this. You have to do this in every line of the tree. So you do C naughts here, and you can remove a bunch of qubits, and you will make this 4 coordinated. So this is done analytically. I'm claiming that these are like type 2. So the standard X cube model, if you put it on this Arboreal arena, becomes effectively type 2. That's what I'm saying. I don't know how, we have not looked at taking Haas code and putting on this. We have not studied that, if that's what you're asking. Yeah. Yes. I think that if you are on tree box tree, then this topological order will die. Reason is these fellows can move freely in this direction, right? In the manifold directions, they can move freely. I've not studied this, but my guess is that if you take B3, box B3, I think it'll be stable. Which is why we are kind of, we are advertising quantum memories and so on, right? Got it. Yeah, so you'll see that I think until k equal to 5, it is continuous. From k equal to 6 onwards, it's discontinuous. Of course, I can't vary k continuously. I mean, we don't have enough. I mean, in this variational wave function only pick up, mean field of what? Of a manifold? Like?
No, I mean.
By mean field. If you do the full calculation, I don't know the answer, right? So the variational wave function we are constructing is the standard one, right? I mean, we'll do this. And that's our parameter, and that does this. That will give you only mean field. It can't give you anything else. So I don't know the answer to this.
If not, let's thank Vijay once more.
Thank you, and thank you so much, Adit, for helping me out.